Buenos dias. Welcome to the Caribbean. Welcome to Puerto Rico. We're going to go over the homework solutions together. I hope it went well for you. I hope we're kind of starting to pick up the pace a little bit. And the homework, hopefully, there's some that are fairly mechanical that help you work through the process, but then some others that you'll encounter some difficulties or some interesting situations. So let's go through it. Our first assignment we're dealing with real numbers, was to look at the various sets of numbers or subsets of the real numbers and properly denote the set relations between each other. Or in other words, are they a set or are they not a set? So the first, we'll deal with the natural numbers. If you recall what those were, just for a reminder, we're describing it, defining it as the set consisting of the counting numbers 1, 2, 3, 4, 5, 6, on and on indefinitely. So is the natural numbers, are they a set of the integers? And again, the integers, we'll briefly reintroduce those. Those are the numbers going like the counting numbers, but including 0 and working infinitely in the negative direction. So negative 4, negative 3, negative 2, negative 1, 0, 1, 2, 3, etc. And if you recall the lesson, we actually had another set kind of between the natural numbers and the integers, namely the whole numbers, which were essentially the natural numbers with the additional element of 0. For the homework purposes, at least for this portion of it, we're kind of ignoring that and we're lumping the whole number since it is a subset of the integers and it's really only one element different from the natural numbers. We're ignoring it, but it's in the back of our mind right now. So are the natural numbers a subset of the integers? Well, yes. In fact, they are the positive portion of that. Okay? Are the natural numbers a subset of the Q? What was Q? Oh yeah, for quotient or irrational number. And just to reintroduce those again for the homework, we're describing the rational numbers as the set of all elements A over B such that A and B are integers and B is not equal to 0. Why is B not equal to 0? Well, you can't divide by 0. Or commonly what we refer to as fractions. So are the natural numbers a subset of the rational numbers? Well, yes. It looks as though possibly not. As we're looking at fraction form, the natural numbers are kind of these whole, non-fractional type numbers. But as we mentioned before, all the natural numbers are in fact fractions and can be written as fractions. Just for example, 1 could be written as 1 over 1, or 2 over 2. There's quite a variety of ways to do so. So the natural numbers are a subset of the rational numbers. All the natural numbers can be written in the form A over B, where A and B are integers and B is not 0. So the natural numbers are a subset of the rational numbers. How about the natural numbers with the irrational numbers? Well, what were the irrational numbers? We'll briefly reintroduce those as well. There's a variety of ways to describe these. For our purposes here, I described the irrational numbers as the set of all elements x such that x is an element of the real numbers, which we've been talking about, but also it is not an element of the rational number. So in other words, if it's a real number, it will either be an irrational number or it will be a rational number. Or another way that we talked about to kind of state the same thing is if the decimal does not terminate or repeat. Remember, a rational number, we're dealing with fractions, we should be talking about decimals as well. All rational numbers, their decimal expansion will either terminate 0.75, 0.324, 0.5, etc., or repeat on indefinitely. 0.3, remember that little repeater sign? Goes 0.333 and never stops. And also, we had mentioned, and I'll briefly mention again, that depending on the particular class or instructor or book you're working through, sometimes the rationals will be described as all decimals that repeat. Now, terminating ones do that as well. As we mentioned, take a terminating decimal 0.5, it does repeat forever based on kind of the trivial 0 that goes on forever. So we can describe it as either decimals, rational numbers as either decimals that repeat indefinitely or terminate. Irrational numbers are decimals that do not terminate or repeat. decimal 4, 3, 4, 5, 7, 3, 4 on. It never stops. So the best we can do is assign a symbol or an operation to it describing it, such as pi or the square root of 2. If we write it out in decimal expansion, all we are doing is approximating, because those decimals go on and on and on. So are the natural numbers a subset of the irrational numbers? Well, no, they're not. And this is in part why I described the irrational numbers as the way I did here. If the natural numbers are a subset of the rationals, which we established they were, then they cannot be a subset of the irrationals, because all rational numbers, decimal expansion, will either terminate or repeat. Irrational numbers will not. So natural numbers cannot be written as irrational numbers. They are not a subset. How about the natural numbers with the real numbers? Well, yeah, all these are going to be a subset of the real numbers. This is how we're introducing ourselves to the real numbers, as the real numbers are the set containing all these various subsets. So the natural numbers are a subset to the real numbers. So the real numbers include 1, 2, 3, 4, etc. All right. How about, let's kind of shift our focus to the integers. Are the integers a subset of the natural numbers? Well, 1 corresponds, 2, 3, keep going, but not 0 and not the negatives. The integers expand in the negative direction. We'll talk more about direction in the next few lessons. But no, the integers are not a subset of the natural numbers. Are the integers a subset of the rational numbers? Well, we said that the natural numbers were a subset of the rational numbers. So what's the difference between the natural numbers and the integers? Well, the 0 and the negative tail, if you will. If tail is an appropriate way to describe that. So can 0, -1, -2, -3, etc. be written in the form a over b, or such that a and b are integers and b is not 0? Well, let's check it out. Let's start with the negatives. -3, for example. Yeah, we could write that as -3 over 1 in the form a over b. A is an integer, -3 is an integer, 1 is an integer. How about 0? We said we can't divide by 0, but we can certainly take 0 and divide it by some other integer. 5, 6, 7, what have you. So yes, so the integers are a subset of the rationals. All integers can be written in the form a over b, such that a and b are integers and b is not 0. Very well. How about the integers with the irrationals? Well, again, we're going to kind of see this pattern. If the integers are a subset of the rationals, they cannot be a subset of the irrationals. How about the integers with the real numbers? Well, yes, again, that's in part how we're introducing ourselves to the real numbers, or by looking at some of the various subsets of number systems within it. So the integers are a subset of the real numbers. So our notion of real number has expanded from 1, 2, 3, 4, 5 to include 0 as number and the negatives going in the negative direction. All right, now the rational numbers. I think this is where we start to have some fun within our lesson when we got to the rational numbers. These ones that can be written as a over b. So how about it? Are the rational numbers a subset of the natural numbers? Well, we mentioned all natural numbers can be written as rational numbers, or in other words, the natural numbers are a subset of the rational numbers. But our rational numbers include far more elements than just the natural numbers. We already talked about how the integers are a subset of the rationals, and the natural are a subset of the integers. So no, the rational numbers are not a subset of the natural numbers. How about the rational numbers with the integers? Well, kind of the same story here. No, the integers are a subset of the rationals, but the rationals include or expand our notion of number in ways that the integers were limited with, namely by allowing for fractions or parts of whole, instead of just one moving either in the positive direction or one discretely moving in the negative direction. Rather, you can go part of the way, part of the one, fractions. So rational numbers, rational numbers are not an element of the integers. Not an element. The rational numbers are not a subset of the integers. I hope I haven't been saying element. Hopefully we're talking about subsets here. How about the rational numbers with the irrational numbers? Well, no. In fact, we've determined, based on their decimal expansions in some of our discussion before, that if a real number is rational, it is not irrational. We can't simultaneously have a decimal that repeats indefinitely or terminates and continue indefinitely without repeating. So if it is a rational, it's not an irrational. If it's an irrational, it's not a rational. So are the rationals a subset of the irrationals? No, they're not. In fact, they don't share common elements. All right, how about rationals? Oops. How about the rational numbers with the real numbers? Well, yes. Again, this is part of how we're introducing ourselves to real numbers. So our real numbers now have expanded our notion of numbers simply from being able to count 1, 2, 3, 4, to adding a 0, to adding negatives, to now being able to talk about parts or ratios. All right, how about the irrational numbers? Now, we won't reiterate kind of what we've done here. We should be able to move fairly quickly through this. Are the irrationals a subset of the naturals? No. One reason among a number is the natural numbers are a subset of the rationals. How about the irrationals with the integers? Again, no, for some of the same reasons. How about the irrationals with the rationals? No, just like the rationals were not a subset of the irrationals are not a subset of the rationals. They don't share common elements. In fact, that's part of what makes them distinctive, are their decimal expansions. So the irrationals are not a subset of the rationals, but they are a subset, which is the whole reason we're talking about them, of the real numbers. Again, expanding our notion of number to include within the real numbers all other decimals, not just ones that repeat or terminate or can be written as a ratio, but decimals that go on and on forever. Decimals that came to our attention by means of finding certain lengths that couldn't be measured, real lengths, but couldn't be measured by simply using rational numbers. If you remember, we talked about looking at finding the hypotenuse of a triangle, or the square root of 2 and the square root of a number of other numbers. The length of the hypotenuse just isn't a rational number. There is no number, a over b squared, that will equal the hypotenuse. And pi was another one. And we also looked at how our imagination can run wild and construct quite with ease all sorts of irrational numbers. So our notion of number, again, has expanded incredibly by the addition or the allowance, the acceptance of irrational numbers. All right, one last thing to look at, the real number relationships to all of these. And we're far enough along, and I think talking about sets and subsets, where we can see that the real numbers are not going to be a subset of any of these other sets. In fact, they are all subsets of the real numbers. I just want to kind of make this explicit in the negative direction. So the real numbers are not a subset of the natural numbers, but the natural numbers are a subset of the real numbers. The real numbers are not a subset of the integers, but the integers are a subset of the real numbers. The real numbers are not a subset of the rational numbers, but the rational numbers are a subset of the real numbers. The real numbers are not a subset of the irrational numbers, but the irrational numbers are a subset of the rational numbers. Okay, now that we noted the set relations between all these number sets, now our next task was to construct pictorially a way that represents these set relations. So there's, of course, a variety of different ways in which you possibly have done this. I'll keep mine fairly simple. Noting what we already discussed, the natural numbers are a subset of the integers. The integers are a subset of the rationals, and then, of course, the rationals are a subset of the real numbers. So we can kind of build that embedded sets, the naturals out the integers, out the rationals. And, I forgot, in this particular homework problem, we're supposed to include the whole numbers as well. So let's start with our natural numbers, n, and I think we can draw it this way possibly to add some clarity to this. in case we forgot, that is a set of natural numbers. Kind of using our Venn diagram, but there's nothing sacred about semi-spherical or round curves, so we're using more box shape. I think it'll be more appropriate for this. Well, the natural numbers were a subset of the integers, so let's construct the integers next. We can put, or excuse me, the whole numbers. I almost forgot about the whole numbers. We can, since all the elements of the natural numbers are elements within the whole numbers, simply by enclosing the natural numbers within the perimeter of our whole numbers, we include all the elements of the natural numbers. What was the other element that was included in the whole numbers and not the natural numbers? 0, right. So I'm putting the 0 down here just so you can kind of see that 0, 1, 2, 3, 4, see how that's going. All right, so the natural numbers are a subset of the whole numbers. Well, the whole numbers are a subset of the integers, and of course the natural numbers, being a subset of the whole numbers, are also a subset of the integers. So let's construct our integer section, and I'm extending out farther this way for sake of our seeing our numbers kind of progress, or our notion of number kind of progressing. These are our integer relations. Although I went too far, we're not going to be able to fit the rational numbers on there. So let me remedy that. Here we have our integers. And what are included? Well, all the natural numbers, all the whole numbers, and also the negatives. So we can have -1, -2, and they go on infinitely in the negative direction. So I hope this is kind of helping you see negatives, 0, positives, see this expounding notion of number as we look at each subset or set relation between all these numbers. So here are the integers. So we have the natural numbers, the whole numbers, as subsets of the integers. Well, the integers are subsets of the rational numbers, and consequently so are the wholes and so are the naturals. So what colors do I have left? Let's use red. To include this is our set. The red set is the set of rational numbers, and those include, in addition to the elements in which are in the integers, the wholes, and the natural numbers, they would include things like 1/2, -3/7, 0.62 repeated, etc. All numbers that can be written as a over b, where a and b are integers and b is not 0. All right, what is our remaining set? The irrationals. Now, where do they overlap? Or where will we just keep kind of magnifying this these outer squares? Well, no, we can't with the irrationals, can we? Because they are not a subset of either. In fact, they are quite separate from all the others. If our rationals are our largest set we're dealing with thus far, and the irrationals are in part defined against or opposed to the rationals, the integers box is going to have to look something quite outside. We could go like this. We're not going to have any rational numbers that are irrational, as the names kind of suggest. And consequently, we're not going to have any natural numbers, any whole numbers, or any integers that are also irrational numbers. So here would be our set I, or irrational numbers, and those would include things such as pi, square root of 2, square root of 15, 0.147336, on and on and on, negative 102.34001, on and on and on, etc. That's quite a wide variety of numbers so far. We've included all of our subsets. Now, with our only set left to properly map are the real numbers. this was part of the benefit for this exercise, I think, is this gives us a visual picture of what the real numbers, we will be working with, really look like. So the real numbers, all of these are subsets of the real numbers. So our real numbers, in this case, are the universal set, or all the elements that are under discussion. Now, if you recall from our lesson, I mentioned that our notion of number expands much beyond just the real numbers. In fact, even in this pre-calculus course, our notion of number will expand beyond the real numbers. But for now on, if we talk about number or numbers without qualification, we're referring to the real numbers, which refers to all of this picture that we see here. I hope your diagram looks something like this, although not exactly like it. You could certainly use different shapes and arrange things different ways. But the subset and set relations themselves should demonstrate accurately the subset nature of the naturals to the wholes to the integers to the rationals, the independent or non-overlapping of the irrationals and rationals and all its various subsets, and the reals encompassing all of this. Pretty cool picture, I think. Numbers are fascinating. All right, let's move on to the next one. All right, next homework problem. To define or describe the real numbers. Well, we just did that. We did it pictorially involving set relations. And there's a variety of ways, if you think about the different aspects of what we've talked about, in which one can describe or define the real numbers. Just to list but a few, kind of how we introduced them as we worked through kind of the talking points of our last lesson, although I got sub-directed a few times. But the real numbers, we could say, are the set of the sets or the subsets of the natural numbers, the whole numbers, the integers, the rational numbers, and the irrational numbers. We also say the real numbers are, save a little writing space, the union, trying to use some of the different things we've talked about, of the rationals and the irrationals. The set of the rationals or the set of the irrationals. We could kind of put into words, the real numbers are the set of all numbers with a finite or infinite decimal expansion. Kind of building on that, using the same idea, just stating it somewhat differently, a little more in line with some of the terminology we'd used in our last lesson, was it could be the set of all numbers with a repeating, terminating, i.e. the rational numbers, or an infinite decimal expansion, i.e. the irrational numbers. Again, stating the same thing. Now, something leading into our next lesson, we could also look at what's a number line, which will be the primary subject of our next lesson. We could talk about the real numbers as numbers that correspond to points on a number line. A little teaser for you so you come back next time. All right, let's move on to the next one. All right, the homework's starting to get fun. Our next task was to look at these various statements and make them true. Decide whether these various items are elements of the corresponding set. Now remember, this is our notation for element or not element. So first task, is 0 an element of the integers? Not of the natural numbers, but the integers expands to include 0 and the negatives. So yes, 0 is an element of the integers. How about the decimal, the repeating decimal, 0.62 repeating, is that an element of the rationals? Well, it's not in the form a over b, where a and b are integers, and b is not 0, but we talked about when we talk about fractions, we can also talk about decimals. So what we could do is convert this to a fraction, like we learned, and see if it can be written in this form. We'll save that for some of the later problems, which I hope you had fun with. No need to do that here because we talked about how rational numbers, the decimal expansion either repeats or terminates. In this case, it repeats. So yes, 0.62 repeating is an element of the rational numbers. Not too bad. Oh, we got negative and a fraction. Oh boy. Negative 2 over 3, or negative 2/3, is that an element of the integers? Well, yeah, the integers include negatives. So this is getting pretty exciting. Got to be an element. Oh, wait. But the integers are only these discrete unanimous steps. Negative 1, negative 2, not parts. So negative 2 over 3, although it's negative, the integers allow for that, but not fraction or not a quotient. So negative 2 over 3 is not an element of the integers. All right. How about -5? Is that an element of the integers? Well, it allows for 0, and it allows for the negatives moving infinitely in the negative direction. So yes, of course, -5 is an element of the integers. How about, remember this Greek letter lowercase pi, which is approximately 3.14. Is that a rational number? Well, the decimal looks like it terminates. So yeah, that's got to be a rational number. We can convert this to look like this form. Wait, that's not what this is saying, is it? We got to be careful with what we don't want to read our own meaning into what's actually there. This is not saying pi is equal to 3.14. It's saying pi is approximately equal to 3.14. This is not what pi is. The more the decimal expands, of course, the closer an approximation we get to pi, but pi extends on. The decimals keep expanding and expanding and expanding on and on and on. So pi, again, which is, we're using this Greek letter to denote the ratio of, regarding circles, perfect circles, the circumference to the diameter. And it cannot be written in the form a over b, because the decimal goes on and on and on and on, never repeating, never terminating. So pi is not an integer of the rationals, which by default, this isn't part of this, but by default, what would that make pi, since pi is a real number? If pi is a real number, not an element of the rationals, therefore pi would be an irrational number, which is one of the examples we used. All right, well, how about this? Here we have a decimal, 0.4375001, ellipsis, inferring that it goes on forever, but no repeating marks. So while the decimal expands forever, nothing repeats periodically over and over again. So that would be not a rational number, but an irrational number. So yes, this decimal is an element of the irrationals. Now, one thing to note, we have repeating zeros here, but just because a digit repeats, if it doesn't do it consistently forever, then that's not what we mean by repeating decimals for rational numbers. We have digits repeat. In fact, we can have a long string of repeating digits, but it will eventually be broken by some other digit. This decimal expands on and on without repeating any particular period indefinitely or terminating. So therefore, it is an element of the irrational numbers. All right, a few tricky ones. All right, this is looking a little bit calmer, no decimals. How about 9 over 0? Is that a rational number? Hey, that looks like it fits our definition of a rational number to a T. It's in the form a over b. We have to check our a and b integers. 9 is an integer, 0 is an integer. We're golden, right? Wait, not quite yet. What's the remaining part? B, the denominator, cannot be equal to 0, which we have here. Why? You can't divide by 0. It's undefined. So 9 over 0 is not an element of the rational numbers. This one is tricky. I hope we read carefully on that. All right, let's look at this one. -121. A negative number, a larger number for the numbers we've been looking at. Is that an element of the natural numbers? Well, the natural numbers expand to large numbers in the positive direction, but don't allow for any negative numbers. So -121 is not an element of the natural numbers. How about 17? Is that an element of the rational numbers? Well, at first glance, it doesn't look like it. 17 is not written in the form a over b. 17 would be a natural number. It would be an integer. It would be a whole number. But wait, we talked about those being subsets of rational numbers. So therefore, 17 would have to be an element of the rationals. And of course it is, because very easily it could be written as a rational number, where the top, the numerator, being 17, an integer, the bottom being 1, another integer, not 0. So yes, of course, 17 is an element of the rationals, as are all whole numbers like this, or all integers are elements of the rationals. All right, how about 0.65734? Is that an element of the irrational numbers? Well, we've got a long decimal expansion, no repeating marks, so looks like irrational to me. No, Damaris is giving the eye. She's right. Just because there's no repeating mark, what is another clue that, or another possibility that rational numbers do as far as decimal expansions go? They terminate. This stops, even though it expands for a while. In fact, it could expand for hundreds and hundreds of digits, but if it stops eventually, it's not an irrational number. Rather, it is a rational number. It can be written in the form a over b. So, no, this decimal is not an element of the irrationals. Okay? About -6/5. Is that an element of the real numbers? Well, this was kind of a gimme, being that we've talked about every set that we're dealing with as a subset of the real. So if this element is, or if this number is an element to any of these sets, of course it's an element in the reals. And so let's see if it is. Well, it looks like a rational number to me. A over b, are a and b integers? -6, is that an integer? Sure is. Is 5 an integer? Sure is. Not 0. It's a rational number. Therefore, it's a real number. An element of the reals. A real number. Okay, how about 7/2? Is that an irrational number? Well, it looks like a rational number to me. A, b integers, b not 0. Rational number, so can it be irrational if it's rational? No, it cannot. So 7/2 is not an element of the irrationals. If we were to long divide this out, or simply divide this out, the decimal would either repeat or terminate. Okay, we're getting there. Hey, we already saw this one, didn't we? 0/10, is that an element of the rationals? No, you can't divide by 0. But wait, oh, that's only if 0 is on the bottom, because remember you're reading a divided by b. You can take 0 and divide it by items, you just can't divide by 0. So does this fit the rational description of a number we're working with? A over b, where a and b are integers. A is 0, that is an integer. B is 10, which is an integer. Check mark on the first part. And b cannot be 0. B is not 0. A is 0, but that doesn't matter. That's the numerator. B is not 0, therefore it is defined, and yes, it is an element of the rational numbers. Okay. Square root of 2. We talked about this one as well. This was the one that gave those folks trying to figure out triangles so much trouble for so long. Which is approximately 1.4142. And I forgot my ellipses. I'm sorry. That goes on. Oh no, I don't need it because I said approximately. It moves. So the square root of 2 is approximately 1.4142, and it goes on and on and on. Is that an irrational number? Certainly is. Not only was it one of our examples in our lesson, and one of the more well-known irrationals, and I wrote subset, it's an element is what we're dealing with, but its decimal expansion goes on infinitely without repeating, without terminating. So yes, the square root of 2 is an element of the irrational numbers. How about, wow, this is kind of an interesting one, -7.45348. And this 348 repeats. Is that an element of the rational numbers? Well, the rational numbers include integers, so the negative portion of it is fine. Decimals are fine, meeting certain conditions. The repeating is good, but what about this 4 and 5? Well, the decimal may start as non-repeating, but it ends repeating forever, 348, 348, 348, 348. So it is repeating. So -7.45348 is an element of the rational numbers. Very good. Now we're going to have some fun with the rational numbers. Next task, we're going to practice, or review and practice, converting decimals to fractions. So here are our particular numbers we're going to convert to decimals. What should our decimals look like? Well, of course, it could be a variety of expansions, but look, they're all rational numbers. So we know our decimals should either terminate or repeat eventually. If not, probably our long division is wrong somewhere, which is a good chance that will happen as I'm working these out on the board. So how do we convert 5/6 to a decimal? Well, remember, one thing that this is saying is 5 divided by 6. So 5 divided by 6 we can simply long divide this out and get a decimal. The 6 go into 5? No. How about 6 into 50? Yes, 8. Not evenly, but it's close. Remember, you have to get as close as you can without going over. 8 times 6 is 48. Our remainder is 2. We don't want a remainder. We can bring down the 0. Does 6 go into 20? Yeah, not evenly, but 3 times. 6 times 3 is 18. Subtract that 2. 0. Oh, this is going to, it looks as though this is going to keep repeating, right? How many times does 6 go into 20? Well, just like it did there, the 6, or 20 divided by 6 hasn't changed yet. So we're going to keep getting this remainder of 2, therefore getting this 3 to repeat on indefinitely. So 5 over 6 is equal to the decimal 0.8, a repeating 3. All right, how about 7 over 8? Again, we can take 7 divided by 8. Does 8 go into 7? No. Well, it does, but not evenly. How many times without going over? 8 times. 8 times 8 is 64. We have 6 left. Bring down a 0. Does 8 go into 60? Goes in 7 times. It's amazing how these multiplication tables change. Or you forget them as you get older. 7 times 8 is 56. Mrs. Foster had to help me out on that one. Bring down the 0. Does 8 go into 40? Finally, this is looking good. 5 times 8 is 40. Now we don't have a remainder. Remember our last problem, 5 over 6, we simply ran into the repeating problem of over and over and over again. The redundancy. Well, in this case, when we come up with a remainder 0, we are finished. Our decimal terminates, unless we consider the trivial zeros at the end. So 7 over 8 is equal to 0.875. Okay, 3 over 2. I hope this is good practice. Some of these techniques that you probably did, but it's probably a long time ago. And you get a little bit rusty. I know I am. So 3 over 2. Well, wait a minute. So far we've been looking at fractions, and we think of fractions a lot of times as like if you have a pizza and you're taking a part of a whole where the numerator is smaller than the denominator. But what is this saying here? Is this valid? Is this okay? Well, the numerator is bigger than the denominator. Well, yeah, of course that's okay. Our picture, if we were talking about pizzas again, would be each pizza is going to have 2 slices. We have 3 of those slices. So we have 1, 2, 3. So we'd have a whole pizza and a half. So 3 over 2, we read the same way. 3 divided by 2. Well, 2 does go into 3, so we don't need the decimal yet. How many times does 2 go into 3? 1. 1 times 2. Subtract 1. Now, we have a remainder, so now we have to get into bringing a 0 down, which means we need a decimal. Down to 0, does 2 go into 10? Yep, 5 times. And good. 5 times 2 is 10. We have no remainder. We know our decimal expansion is done. 1.5. Hey, that makes sense with our pizza drawing, doesn't it? 1 whole pizza and a half of a pizza, or 0.5 of a pizza. So 3 over 2 translates to the decimal 1.5. Next one. 4 and 4/5. This is called a mixed number, where you have a whole number out here and then a fraction here. There's a few different ways you can tackle this to come up with a decimal. I'm going to show one particular way, a way that I think is easy. Let's convert this to what's called an improper fraction. The form that we looked at here, where the numerator is larger than the denominator. So the way, of course, you do that, and we won't draw the pictures out. Again, I'm kind of assuming there's some basis of working with fractions in the past, so I'll just kind of mechanically show you the steps to do this. If you take the whole number, multiply it by the denominator, 4 times 5 is 20, add it to the numerator, 20 plus 4 is 24. That is your new numerator. The denominator, of course, remains the same. So this would go to 24 over 5, an improper fraction, a mixed number. So this looks like something we're working with. So we can take 24 divided by 5. How many times does 5 go into 24? Without going over, well, 4 times. 4 times 5 is 20. Remainder of 4, we need a decimal. How many times does 5 go into 40? 8 times. 8 times 5, 40. Subtract, no remainder. We're good. 4.8. And notice, we should, because our original number is greater than just a fraction or part of 1, it's 4 and then something, not quite up to 5. Our decimal makes sense. We have 4 and then the decimal representing this fractional part or part of the whole. So our decimal makes sense with our mixed number. And we should always look at things to make sure that they make sense rather than just mechanically work through steps and then at the end say, oh yeah, I did the steps, I'm good. We should always look back and see if our answer makes sense. In this case, it does. Okay, last one. -3. Well, how are we going to turn -3 into a decimal? It's not a fraction, but we've talked about where we could take -3, make it a fraction or a rational number. Anything divided by 1 remains itself. We mentioned the uniqueness and the power of 0. When you add it to a number, it doesn't change that number. Well, 1 does the same thing with multiplication and its inverse division. And we'll talk about those in a few lessons from now. They may seem trivial, but they're very important. They set themselves apart from all other numbers by having these properties. So -3 over 1, well, that's easy enough. We can take -3 divided by 1. It's negative. How many times does 1 go into 3? Well, 3 times. 3, -0, no remainder. So, of course, -3. We don't need to go into the decimals. So if we're forced to use a decimal, we can simply put a 0. Now, we didn't even have to go through this. We could just look at this and use our logic and state that because we're in base 10 number system, a decimal, by adding 0, won't change anything. We have a whole, no parts of the whole to deal with, so our parts of the whole are 0. So -3 in decimal form is -3.0. Or we could even get crafty and have that 0 repeat on forever. Well, as exhilarating as it was converting decimals to fractions, nothing compares to the thrill that one can get from converting decimals to fractions. We're going to continue having fun with rational numbers. We're going to do some more practice review converting decimals to fractions. Now, why are we converting decimals to fractions? Remember, rational numbers are numbers that can be written in the form a over b, i.e. a fraction, where a and b are integers, and b, of course, cannot be 0, because the math universe explodes or implodes, however you want to think of it, if you attempt to divide by 0. It's undefined. So our first one, 0.4. We're supposed to translate that or express that as a fraction. And I just noticed I wrote my heading up here wrong. We're going from decimals to fractions. All right. So, it's supposed to look like this, with a and b as integers. Well, what does 0.4 represent? Again, assuming some basic understanding of a base 10 number system and what the decimal 0.4 represents, we know that this is the tenths spot, and how many of those tenths are being represented? Well, 4 of them. So here is a perfectly good rational number in the form of a fraction. But, like always, we want to reduce these the best we can. So, but just to clarify, this is correct. A and b are integers. 4 is an integer, 10 is an integer, and it is in the form a over b. B is not 0. But when we're dealing with fractions, we typically, almost always, want to reduce it to its simplest form. So in this case, 4 over 10 can be reduced to, divide both of these by 2, 2/5. And again, a rational number, a and b are integers, b is not 0. Very good. Next one, 0.22. All right, a little bit more challenging. We have an extra digit into the what? The tenths, the hundredth spot. So that helps us figure out what our denominator will be, 100. And how many 100s are being represented? Well, 22 of them. So here we have a number, a over b. A and b are integers, b is not 0. That works, but what do we want to do? Yes, of course, we want to simplify or reduce, and we're using those terms synonymously here. So we can divide what goes into 22 and 100. Well, 2 does. Pick easy ones for us. 22 divided by 2 is 11. 100 divided by 2 is 50. 11 over 50, and that's as simple as we can get it. So again, a rational number in the form a over b. A and b are integers. B is not 0. We're doing pretty good. 0.72 with this bar, remember that means it repeats on and on and on, so we could have 72, 72, 72. Excuse me. All right, so we're kind of getting used to these. So how would we translate this into a fraction? Well, we need to look at how far the decimal expands and use that as our base for our denominator. But oh yeah, this was the problem. This expands forever, so we can't do what we did here because it doesn't stop simply at the tenths or the hundredths or the 100,000ths or etc. So remember, we had to use I won't say a clever trick, but clever, careful thinking. Our problem was that this tail goes on forever, so our former technique won't work. So we looked at a way in which we were able to get around that, and we used algebra. So again, if we're going to kind of work through this just step by step. If you want a little bit more of the explanation, I'd encourage you to go back and rewatch or watch for the first time our lesson on this. But what we do is we can set this up as an equation. When it's an equation, where this is just a number, we're kind of stuck. This is what it is. But an equation allows us to use the rules of algebra to maintain an equality, but manipulate it such into possibly a better working scenario where we can get around the problem we were initially stuck at. So we can say, Dama, pick a variable, a letter for us, or a Greek letter, or anything you would like.
S.
An S. All right, so we'll let S equal 0.72 repeating. And remember, our goal is to get 0.72 repeated in the form of a over b, where a and b are integers, and b is not 0. All right, so here we have an equation, an equality. S is 0.72 repeated. So, Dama, what is another way to say 0.72 repeated?
S.
S. You got it. Sable, what is another way to say S? Very good. 0.72 repeated. That's important to keep in mind. So now that we have an equation, we can use the rules of algebra. Again, remember, we don't just arbitrarily choose something or follow a step to get through this. Our goal was to get rid of this tail. So one thing we noted about multiplying decimals by powers of 10, since we're working in a base 10 number system, is if you multiply this by 10, it'll essentially move the decimal one spot over, 7.27, and that will repeat. But if we multiply it by 100, because this is the portion that repeats, it extends into the 100th spot. If we multiply this number by 100, the decimal will be moved here. And again, remember, we can expand this number numerically by continue writing out 2 sevenths. So that will be very helpful for us. It'll allow us some possible options. So we'll multiply both sides by 100. 100s is equal to 72.72 repeated. And I guess just for clarity's sake, I'll write the step up here. What we did was we multiplied by 100. We multiplied by 100. And so now we have an equation. Again, it's still balanced. If you remember our bench press example, our weights are still balanced. They're just different. So we have 100s equals 72.72 repeated. All right, remember the goal, this is the problematic area. If we can get rid of that, well, now we can. All we have to do is subtract. We can subtract 0.72 repeated from this number, and that will take care of this nicely. These just drop off. We're taking 72.72 unrepeated, subtracting 72 unrepeated. Those will cancel out. So we're left with 72. Hey, a nice number, a whole number, an integer that we can work with. But we can't just leave it at that. What we do to one side, again, we have to do to the other side. So what did we do? We subtracted 0.72. Well, Dama, what's another way we can say 0.72? S. Yeah, S is the same thing. It's equal. So since we have an S over here, and we want to get rid of that anyway, let's subtract S. Now we did the same. We did the same operation and quantity on both sides. It's just represented differently. S is 0.72 repeated. So if we subtract S from 100s, we are left with 99. S. Oops, should use white to stay consistent. 99S. All right, now to get the variable by itself, divide by 99, right? 99 divided by 99 is 1. 1 times S is simply S. That will essentially get S by itself. But we have to do the same to this side. Divide by 99. What do we have? This looks like a rational number to me. So S is equal to 72 over 99. Now, what was S? Another way to say S, Dama, one more time.
0.72.
0.72 repeated. So we're just going to substitute that in. 0.72 repeated equals 72 over 99. Look what we have. Exactly what we're going for. We converted a fraction, or excuse me, a decimal. I got to get that straight one of these times. A decimal to a fraction. The rational number 72 over 99. It's in the form a over b. A and b are integers. B is not 0. But in this case, it looks like we can reduce to a simpler form. So let's go ahead and do that. 0.72 repeated is equal to, what can we divide both of these into? Well, 9. 72 divided by 9 leaves us with 8. 99 divided by 9 leaves us with 11. So again, we have our original decimal expansion is equal to the rational number in the form a over b, where a and b are integers and b is not 0. Excuse me. 8/11. Now, this was quite a few steps. If we wanted to go back and check to make sure we did this correct, what would we have to do? Yeah, let's long divide this out. And this is the only one we'll do this with, but it's always good to check your answers, so we'll do it together. So to convert a fraction to a decimal, we just spent time doing that. One way to look at this is we're saying 8 divided by 11. How many times does 8 go into, or 11 go into 8? 0, you need a decimal. How many times does 11 go into 80? 7. 77. 3 remainder. 0 comes down. How many times does 11 go into 30? Well, twice without going over. Hey, that's looking good so far. 2 times 11 is 22. 8. All right, we see immediately that this process is going to go on forever. We checked our work. We're good. I think we're ready to try one a little bit more challenging. Let's convert 2.431, where the 31 are the repeating portion of the decimal. This 4 doesn't repeat, so we can expand this as 31, 31, 31, and so on. Now, our initial strategy, or our last strategy we used, appears that it should work here. Or this is our problematic area. If it was simply 4, we could put this over 10, or convert this to an improper fraction. If it was simply 431, we could again use it, extend it to the thousands place. But where this keeps on going and going and going, this repeating part is a problem. So we need to attack, we need to get that out, and utilizing the rules, the abilities of algebra to do so. So first thing to do, again, is to set up an equation. Dama, one more variable. Okay, very good. We'll let G equal our number 431 repeated. And again, is this a rational number or an irrational number? Yeah, rational, right? If we're converting it to the form a over b. This is a rational number. Remember, rational numbers, decimal expansions either terminate or repeat on forever. Okay, so what we've been noticing is if we can move the decimal on the number to the right of the repeating portion of the number, we've had success. So I think we can do that here. If we multiply this particular number by 10, 100, 1,000, that should help us, right? So let's do that. We'll multiply both sides by 1,000 to move this decimal, and it'll give us a little wiggle room, so to speak. All right, 1,000 times G is 1,000 G, which is equal to, and this will go boom, 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 And remember, this 3, 1 repeats all the way forever. So we now have 1000G is equal to 2431.31 repeated. Now, we've seen enough of these, I think, to notice that we can simply subtract this tail end and be in good shape. But look, something's a little bit different here. Well, we originally let G stand for 2.431. If we subtract G from both sides like we've been doing, we're going to run into a few problems because this isn't 0.31 and we can simply move the tails off. This is 2 with this extra 4 here. So let's not panic. Let's critically think through this. We've moved decimals around before. We notice our new problem is essentially this 4 is in the decimal spot. We just want to deal with the repeating portion to be able to get this repeating portion off. If we simply subtract this from here, this 4 will be underlined over the 3 over the 1. That's going to be a disaster. It's not going to accomplish what we need it to. So our problem is this 4. It would be nice if we could have the decimal, strictly speaking, be 0.31 repeated. So how do we do that? Well, based on what we've learned, or what the skills we've been using, we've been moving decimals fairly easy and fairly effectively. If we multiply this number by 10, we would essentially have 24.31 repeated, in which case we could subtract and the 1 repeated would drop off. That sounds like it'll work great. So instead of subtracting just G in this case, if we subtract 10G, and I'll write it over on this side first, 10G, then we will be able to subtract this off. So what is 10G? Well, if this is, I'll do a little side note over here, if G is 2.431 repeated, and we take 10G, 10 times this number, we'll move the decimal over, so 10G will be equal to 24.31 repeated. So we're subtracting 10G from this side, 10G from this side, but we don't have a G over here, so what's another way we could express 10G? Exactly, 24.31. 10G it's equal to 24.31. Another way we can express 24.31, 10G. So we can subtract from this side 24.31. Now, just to make sure we haven't broken any algebraic rules yet, we've done to both sides hopefully the same operation and quantity. We've subtracted, okay? We've subtracted 10G and 24.31. Well, 24.31 is what 10 times G would equal. So we are good. So now all we're left to do is to subtract. 1000G minus 10G would be 990G equals, well, what do we have here? This is where it's important to keep nicer penmanship than I do, so we can keep everything straight. Subtract, those are going to be 0 like we've been seeing. All right, 1 minus 4 we can't do, we'll have to borrow. Take you back to good old 2nd or 3rd grade or first, whenever it was that we learned these type of tricks. Or not tricks, tricks is not a very good word at all, but these techniques. So 11 minus 4 is 7. 2 minus 2 is 0. 4. So 2,407. Are these decimals subtracted off? All right, this is looking great. All that's left to do is divide, get G by itself. Because remember, we've already established G by itself is what we're attempting. So divide by 990. 990 divided by 990 is 1. Anything divided by itself is 1 times G. Keeps G remaining the same. So G is equal to, I'll use white chalk. G is equal to, what do we have to do? We did to this side, we have to do to this side, 990. So G is equal to the ratio of the integer 2,407 and 990. A number in the form A over B. A and B are integers. B is not 0. So here we have, again, what was G? G was 2 point, so we'll substitute in 2.431, the 3-1 repeated, and that is equal to 2,407 divided by or over 990. Pat yourselves on the back. That was a good one. We used a few problem-solving strategies to get through that, and we have successfully converted a rational number in the form of its decimal expansion into its form as a fraction or a quotient. Well, that last one was certainly a challenge, but let's see if we can solve this one. This one looks even more frightening than the last one did. Look how long the decimal expansion is. 0.1277435 going on. How are we going to tackle this one? We have nothing to use our first technique with, that is placing the denominator as the spot it represents, because it keeps on going forever. We don't have any repeating part either to take off to use our second technique. So what are we going to do? Yeah, Damaris, very good. Before we panic, we should look at and always critically think through what is it we're trying to solve. We can't convert this to a fraction. Why not? A fraction is what? A rational number. A rational number's decimal expansion either terminates, stops, or repeats. This does neither. This is not a rational number. This is an irrational number. So we cannot write it in the form, a over b, where a and b are integers. We just can't do it. It's an irrational number rather than a rational number. I hope you caught that as you're working through these. One more to go for this portion of our fun converting decimals to fractions. 0.9 repeated. After those last few challenging ones, it's kind of nice to see just the regular repeatings aren't that scary anymore. We just have one digit to work with. We should be able to breeze through this. So let's go with it. Damaris, pick a variable. Enye, very good choice. A Spanish letter we'll use as a variable. Did I say that correct? Enye?
Enye.
Enye. And that is, for any of you who are missing out on a whole lot from life by not taking Damaris' conversational Spanish series, you would have learned that the enye makes the ny sound, and it's a letter unique to the Spanish alphabet that is not, or I don't know if it's unique to the Spanish alphabet, but it's not in the English alphabet. And it looks like we'll use a lowercase one. It looks like this. So enye, remember, it's just a variable. We could draw a picture of Valentine or a goat, as we've done in the past if we wanted, or a gerbil or whatever. But enye is equal, we'll let that be equal to 0.9 repeated. This is what we want to solve. All right, we're pros at this by now. If we multiply each side by 10, the repeating portions just into the tens, it's nines all the way, we should be home free. So we'll multiply both sides by 10, and we get 10 enye is equal to 9.9 repeated. All right, this tails our problematic area. We can take that off. We can simply do what? I guess I'm in yellow chalk now. We can subtract either an enye or a 0.9. It's the same thing. It's equal. It's just whatever form is more convenient for us. In this case, we'll use the numerical version. So we'll subtract 0.9 repeated. And in this case, we'll subtract an enye. Remember, we're doing the same. 0.9 repeated is equal to enye. So if we subtract both of those, we are left with 9 enye, looking good, is equal to, these will cancel out, 9. Hey, we're home free. All we have to do now is to divide and get the variable by itself and substitute, and we're good. So we'll divide each side by 9. The yellow chalk's not working too hard anymore. And we are left with enye is equal to, what's 9 divided by 9? Uno. Okay, no problem. It's an integer, or it's a rational number in the form a over b. b is not 0, so we're fine that way. But what's our problem? This isn't what NA equals. We start out with NA equaling 0.9 repeated. Is 0.9 repeated equal to 1? Well, we followed everything fine. We've obeyed the rules of algebra, and we come up with a statement that says 0.9 repeated is not close to, but it is equal to 1. An apparent paradox. Interesting. Now, this problem was intentional. Algebraically, we showed that 0.9 repeated is equal to 1. Is it? That's the question. Now, this is discussed, this is debated, and I won't enter my for whatever my 2 cents are worth on kind of where I fall on that. But what is this saying? Is it, in fact, one possibility is, hey, we simply take this at face value. It may be an apparent paradox, but this is simply what it is. 0.9 repeated is equal to 1. Is it that? Or is it showing that algebra is somehow flawed and that it is inadequate to deal with this? Is it showing possibly some of the interesting nuances when looking at infinite items from a finite perspective, or looking at finite items from an infinite perspective, or looking at infinite items from a finite perspective? Or is it some combination of those? This is certainly an interesting debate, and it's way beyond the point of, or the scope of our discussion to get into that. I'm sure a little research on the internet, you'll get all sorts of, maybe some passionate expounders of one of those versions from the other. But this is something interesting. Algebraically, 0.9 repeated is equal to 1. So is it? Is it not? Does it let us know something about the infinite? But this, to me, when I first was approached with this really got me curious, and this got me into a world of Cantor dust and all sorts of very interesting things. And coincidentally, or not coincidentally, it led me into exploring sets and basic set theory with enthusiasm for the first time. So it's appropriate, I think, to end this portion of our assignment where dealing with something like this leads, at least for me, and I think if you follow the rabbit's trail through enough items, will lead you to get into some of the development of set theory and some of the amazing fundamentals of it and some of the unexpectancies that come about. But this is quite an interesting result. But if this is what you came up with, you did it right. It's the solution that now requires some thinking about. So if nothing else from this problem, next time you're hanging out with your friends or your family and you ask them, hey, is 0.9 repeated equal to 1? You'll probably get a lot of no's, and that may be a fair result. Again, I'm not weighing in on this, but you can say, hey, I can show you where it's actually equal to 1, and you can work through this process. So some good conversation piece for you there. All right, we'll leave our fun with converting decimals to fractions. I hope this stays in your mind, and I hope you can't get rid of it. I hope it drives you further and further and further into the amazingness that the mathematics allows us to think about. Last portion of the homework. Consider if and how your notion of number has expanded. I won't answer that or discuss that. You've had enough of me talking about that. I'll leave that for you. And also, looking forward, how might our notion of number expand beyond the real number? So far, we've just discussed the real numbers. We've looked kind of practically, very informally through history, but very practically about how our idea of number has expanded and developed due to practical needs, through measuring or numbering or all these sorts of different things. So with our notion of real number, how might that expand? Practically or perhaps algebraically? Again, in this course, we will see even our notion of number expand beyond the idea of real numbers out of necessity for quite a different reason. But this is a good chance for you to really sit down, reconsider number, reconsider what you associate number, think about how it has expanded, if it has, which I sure hope it has. Mine does every time I contemplate these things. And think about some of those developments and how from the real numbers, what might be some circumstances or stimuli to help our idea, our notion of number expand and develop even beyond that. Look forward to seeing you next lecture as we'll continue discussing real numbers, and we'll offer another way to describe or define real numbers, and we'll look at the real number line. Look forward to seeing you then. Have a great afternoon.
Thank you for learning with the Fosters. This is a friendly reminder. Remember that these courses are not for free. For information of the cost of the lessons and how to pay, please visit our website. Thank you so much for being with us.